Okay, so welcome to this new video in which we are going to learn about the introduction, a gentle introduction to the higher order linear differential equation. And we are going to talk about how the equations are important in our day-to-day activities, day-to-day mathematical activities. And also, I'm going to introduce you to the operator, the linear differential operator over here. Okay, so the motivation behind using linear differential equations of higher order is to model a particular situation, a given scenario in terms of the rate and the quantity of the particular, uh, the dependency of the variable on an independent candidate. Right. So basically, there is a independent variable and there is a dependent variable, and the dependent variable is changing at some rate based on the independent variable, and that is what we model over here. We want to solve these particular equations, and well, these are all ordinary differential equations, and it's called ordinary because there is just one independent variable. If suppose there were more than one independent variable, then we would have gone for a partial differentiation. Okay. Now, of course, we are talking about differential equations because differential equations capture the variability of the particular dependent variable over the independent variable. And finally, the last term of here we must understand is the term called higher order. And this higher order is actually, trying to encapsulate the different types of variability of the dependent variable as we change the independent variable. Okay, cool. Now, the linear differential equation is an equation involving a dependent variable and its derivatives. Okay. Now, this dependent variable, we represent that by y in this particular, in this particular grammar that we have written here. So we represent the independent variable by x, and as you can see on the right hand side, right? So y is a function of x, and this y is written, and that is written as y. So y is the dependent variable, whereas x is the independent variable. And since y is the dependent variable, the changes of y are dependent on the changes of x, correct? And those variabilities are encapsulated in these derivatives. So the first one is a first order derivative. The second one is a second order derivative. The third one is third order derivative, and so on. Please note that the derivative of order 0 of a particular dependent variable is that dependent variable itself. I have not mentioned that because it is pretty obvious, but it's an important point. Another important pointer that we must keep in consideration here is that we are considering non-fractional. I mean, this should be all whole numbers, right? So there can be 0, 1, 2, 3. When we talk about the order of differentiation. Okay, now the linear differential equation contains this y and dy dx, d square y by dx square, dqy by dx cube, and so on. But in the linear differential equation, these like the degrees of y, dy by dx, d square y by dx should all be equal to 1. If these become more than 1, or some of them become not necessarily all of them, but if even if one of these numbers are not equal to 1, it becomes non-linear. Well, and there is another condition that all of these terms y and dy by dx and d cube y by dx square and so on, these cannot be multiplied with each other. There can be a linear combination of this, 5 times, for example, 5 times dy by dx plus 7 times d square y by dx square. So that is fine, but both of these multiplication multiplied together, that is not allowed. Okay, so the general form of a linear differential equation is given as d power n y by dx power n. So that is the nth order derivative of y plus p1 times n minus 1th time derivation, and so on, all the way up to pn the zero derivative of y is y itself, and that is equal to f. And here this y, p1, pn, and f, all of these are functions of x only. They do not have any y in them. All right. Now, here we would want to, like in the beginning, we would be trying to solve some linear differential equation with constant coefficients. And at a later stage, we will come to linear differential equations with variable coefficients. And actually, the method to solve the equations, the linear differential equations with variable coefficients, is to basically reduce them. Put some kind of substitutions, like exponential substitutions. We'll be dealing with Cauchy and legendary linear differential equations. And in those equations, we substitute a particular monomial by e power t, right, to an exponential variable. And then we convert that again into constant coefficients. So we'll first learn how to solve the linear differential equation constant coefficients, and this is the homogeneous linear differential equation with constant coefficients, right? So the right hand side is 0, and all the constants are, all the coefficients are constants. And since we have a homogeneous one, there is another equation which is a non-homogeneous one, where the right hand side is a function. It's a non-zero function. And again, this function is of x only. There is no y on the right hand side. We are not dealing into, we are not delving into those type of differential equation as of now. It's outside the scope of this video. Okay, now y is the unknown quantity, and we are all fighting to find out what the value of y is, or what the expression of y is, right? Okay, now there is a theorem over here that I must let you know. The theorem goes as follows: that if there is a linear differential equation and y1 and y2 are two solutions of them, then a linear combination, c1 y1 plus c2 y2, is also a solution of the linear differential equation. Now, these values C1 and C2 are constants again. So, a constant multiplied by the first solution plus constant multiplied by the second solution is also a solution of the equation. And please note that this C1 and C2 are arbitrarily chosen. It's not that that this is true for some specific values of C1 and C2. This is true for universally every constant C1 and C2. Okay, the proof is pretty simple. I leave it to the viewer to actually solve it, write it down. So, since y1 and y2, just as a sketch of the proof, since y1 and y2 are solutions of the linear differential equation, we can just, take the linear combination of both of the left hand sides of this equation with y1 and y2 substituted one after the other, and we can find out by the properties of differentiation that indeed the linear combination is a solution uh, of the linear differential equation that is given to us. Okay, now we'll look at what the operator is, and we'll see an example at the end. So you see, what we do is that we define d, capital D, as small d by dx. You see that this is not exactly a complete function, but this is kind of a mapping that we are doing from the space of functions to the space of derivatives of the function. So d, capital D, is the mapping to the first derivative, and the function d squared, the operator d squared, is a mapping to the second derivative. And like from here we can very easily write that dy is equal to dy by dx, and capital D squared is equal to small d square y by small dx square. And substituting these values, we get this particular equation over here, where the right hand side is 0, right? So you see that the cumbersome looking equation now takes a very beautiful form. And since this happens with the homogeneous one, we can do this with the non-homogeneous one, which follows a similar principle. And the only difference here is that in the non-homogeneous one, the right hand side is f. And also, we can go a step further, and we can take the y out, right? And we can have, like the left hand side bracket in which we can look at an algebra of all the operators here, right? So the algebra means a product and summation, and that's exactly what we see here. So this is the general form of a non-homogeneous linear differential equation in the operator format. Okay, now let's take an example and let's see what this equation looks like in the operator format. The first thing to do is to find out what is the independent variable and what is the dependent variable. So the equation is d squared x by dt squared plus 5 times dx by dt plus 6x is equal to 0. So you see, a very easy way to understand which is the independent variable is by looking at the denominator. So in the denominator, you find that there is a t. So since there is a t in the denominator, t is the independent variable and x is the dependent variable, as you can see over here. Now, so immediately what we can do is that we can write dx by dt, right? This as equal to capital D small x and d square x by dt square as capital D square small x, right? And yeah, so this is how we do it, right? And this gives that, once you substitute the values over here, the first one becomes d square x plus 5 dx plus 6x is equal to 0, and we get d square plus 5d plus 6 multiplied by, so it's not a multiplied by, it is an off function over here. Of x is equal to 0. I mean, writing the t here is maybe, you might want to skip this t from here, but just for the sake of clarity, more robustness, brevity, I have mentioned it there. Okay, thanks for watching. We'll come back on a next video with more details of how to solve various types of linear differential equations. Thanks for watching.